Hello everyone, good afternoon. My name is Malhar.
I'm Mitul.
We'd like to talk further into this last chapters of the book. So, one of the chapters in the book has something to do with the periodic table. Now, all of us have done GCSE chemistry, and kind of aware. So, all of us have heard of the periodic table. All of us kind of know what it does. So, what the periodic table does is sort different elements into different groups. Now, the periodic table works with mass. So, there's something quite similar to it in physics, but also quite different. This is a standard model, and it's quite similar to something you'd encounter in life. So, who here has ever built a Lego set? Don't be ashamed. We've all done it. And when you have a Lego set, you never have a brick that's the size of what you're trying to build. You always have bricks that are smaller than what you begin with. And by putting those bricks together, and different kinds of bricks, different colors and different shapes of bricks, you eventually end up with your model. And now, in physics, there's quite a similar thing. But the problem has been, and we still are figuring out, what's the smallest brick that you have in the set? Now, first of all, we came to the idea of an atom. The atom being the smallest thing, it's like a little marble, and you can stack those marbles to different shapes and get different materials. But then Niels Bohr, the person mentioned earlier, along with lots of other pioneering scientists, eventually found out that we can further split it up into three smaller components: the proton, the neutron, and the electron. Now, again, for a long period of time, between that and but more recently, we thought that has to be it. That's it. Can't split it up even further down. And then we came to this. So these are quarks on the top, leptons on the bottom, and bosons on the right. These make up protons, neutrons, and electrons. So protons and neutrons are composed of up and down quarks, while the electron is right there, which is a bit odd, and we'll come to that in a second. Now, as you learn in the year two side of physics, a proton is two up quarks and a down quark, and neutron is two down and one up. And similar configurations give you all the different subatomic particles that you have. But on the right side of the standard model is where things get really interesting. That's a photon, and it's here as a particle. But we just saw that photons don't have mass, and they don't exert all the properties particles does. And photons exchange particles here. They mediate how all of these interact with each other. And same thing with gluons. Gluons hold quarks together so that they can form bigger structures. Otherwise, you'd only have up quarks and down quarks and strange quarks all isolated to each other. Now, the W and Z boson. W and Z boson have to do with annihilation, when antiparticles and particles come together and they release energy, but they cease to exist. And the Higgs boson is kind of an outlier because it gives every other subatomic particle its mass. And that has to do with a lot of complicated things that I don't understand either. So once I learn that, I'll get back to you. This is the Lagrangian equation. It's famous for one, being the longest equation in physics, and two, being the only way you can mathematically explain the standard model. And yes, this is one whole equation that explains this picture, but very accurately. And this atom that we've built up from all these little Lego bricks, it can explain a lot of things. But these are the things it can't explain. Why do they exist? Why only 12? Where does gravity come in? We didn't see a graviton. And what about dark matter? We've all heard about it. We know it exists. We can see its mass and how it affects how quickly galaxies spin. But it's not explained here. And like a model, and like the sheet model, all models have limitations, and this is one of the limitations. Pass on to Mitul.
This is one of the most famous pictures of all time. This is the picture of a black hole.
Illustration.
Illustration, the actual pictures.
We couldn't get it big enough.
So this is what a black hole looks like, obviously viewed from afar. There you see the big black pit which sucks everything in. Now, again, let's get back to how black holes are formed. So when a star it's burning and when all of its hydrogen and helium have been extinguished, it collapses under its own weight and then it falls so deep down in space-time, it creates like a dip which is so dense that it pulls everything around it. Now, again, since space-time is curved, everything that goes near the black hole or crosses the event horizon, it gets sucked in, even light. So nothing can escape. And just like light, even time slows down close to the horizon. And when things get really interesting is when we enter the black hole. So imagine you're entering the black hole, and this is assuming you don't get spaghettified. This is one of my favorite words of all time, spaghettified actually. It's when the gravity at your head and at your feet, the difference is so immense that your head and feet, they get split apart, they get stretched. So, and it basically spins you around and makes little like spaghetti strands out of your body. But the good thing is you don't feel it. You don't have enough time to feel it. And imagine you get sucked in. Now, a black hole is shaped like a funnel. Starts wide at the start, and then as you go down, it slowly compresses. Now,
Oh, there you go.
oh yeah. So, yeah, as we reach the singularity, which is where the fallen star actually is, this is called the Planck width. This means that the black hole cannot get thinner than this. So let's say we begin our journey down the black hole. We get down, 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 down. And just as we are about to reach the singularity, the black hole jumps. Now, what does it mean when I say jump? It's sort of like a kind of unexplained phenomena, because the black hole now it can't shrink any further, so it has to expand. But how does it do that? So it jumps through space and time, it travels through another dimension and comes back, and now it suddenly becomes a white hole, where everything inside it, apart from the gravity, is reversed. Yeah, everything inside it is reversed. Now, you are at this point. Now, since the white hole, everything is reversed, you will begin to rise out and millions of years into the future, even billions. But this entire process of you getting sucked in, reaching the singularity, then getting back out, this takes less than a millisecond. So, essentially, this black hole white hole system works as a time capsule. So basically, if you like, so basically, again, this entire structure is obviously not three-dimensional. It's not even four-dimensional. We don't know what it is. And this structure, it manipulates space-time in a way Einstein's general relativity could not explain. So that's the reason why Einstein had this huge feud with quantum mechanics. It's like, okay, how can this work? How can my equation explain what's going on at this point precisely? He said that his equations could explain white holes. You just have to make the time variable negative. But his equations couldn't explain how the jump actually took place. And we still can't. Because quantum gravity, it's a topic which no one really knows about, because no one knows anything about, because like Malhar said, there's no gravitons we can detect, because gravity is a force. It's a force which only acts on large objects, and so just like what I say, zooming it is impossible.
Scaling it down.
Yeah,
to
scaling it down.
size. Yeah.
Is
So us are here because obviously we know about this word, and we like to learn about this word, maybe not always, maybe not all the time. But what's really interesting is how we learn physics and why we study physics. So physics is essentially a tool. This is a tool from which we find out more about the world around us. And we try to understand it, not just what we have found out. One of Einstein's favorite quotes is there's only two ways to live your life. One is through nothing is a miracle, and other is through everything is a miracle. And you can either way, miracles exist, one miracles don't exist. You live your life, and while you live your life, you see things. You see things, and you don't forget them. You think about them. And when you think about them, the things that you have learned and the things you've seen all over your life, you start to process them together. And then you use tools like critical thinking, analyzing all the information, and physics. These tools compile all the information that you've learned, and you start forming assumptions about information that you haven't learned yet, information that you haven't been able to see yet. You record all of this down in some way. You can talk to your mate about it, or you can write a book about it. And once you write this information down, it's immortal. As long as this piece of paper stays, it's the information and all your thoughts are going to stay with it. Now, physics as a subject, once we get into it, once we start learning it, we'll quite often encounter things that haven't been explained, aren't explained fully, or just people just don't know about. And quite often it's a struggle between what you should learn and what you shouldn't learn, what you should invest your time in. And there's lots of brilliant minds who have wasted their lives away working at things that had no answer or had an answer that was mundane and uninteresting. The more we learn, the smaller we get. Before, we thought Earth was the center of the universe and the sun, moon, and stars revolve around us. But then, there was a whole struggle of that being proven wrong. People killed, blood spilled. But as that happened, we only realized that we were getting smaller. We then built bigger telescopes, so further out, and saw the immensity of the universe. And because we saw it, we only realized that we're getting smaller. Another interesting topic that we found out throughout this search is entropy. Now, if I could arrange a quick demo about it. So, I've got a cup of coffee. At one point in time, it was quite warm. Now it's lukewarm. And energy likes to spread out. The second law of thermodynamics states entropy, a mysterious one that we'll get to, can only ever increase in a system or stay the same. It can't decrease. What that means is this cold cup of milk and this hot cup of coffee, once I mix them, at this point in time, they're half mixed. They aren't completely mixed. So there's still coffee at the top, milk at the bottom. But as I keep on adding milk, and if you look at the table as a system, it still has a cup of milk and a cup of coffee and two different cups. And the first cup doesn't have any milk in it, and the second cup has all of it. And now the milk and the coffee are irreversibly mixed. And there's no way that we can get them to mix back into coffee and milk. But the reason they mixed and the reason they combined is because of the random motion of particles. The particles moving around, they bumped into each other, and they spread out. But this all happened randomly. And God doesn't play dice, and this is a game of dice. So there must be some dice roll that happens that gets it back into settling out as milk and coffee. But we don't see that happening. And we'll have to wait the age of the universe for that milk and coffee to separate, if at all. So you can think about the initial state of the cups of milk and coffee as the Big Bang. In the Big Bang, you had lots of particles and lots of energy concentrated onto a single point. Now, the single point was very small, and now in the time we're living, the universe expanded into a ginormous size. So obviously, there's been some spreading out. Now, because there's been spreading out, and energy can only ever spread out. It can't spread back in. It can't ever collapse back into the point we had in the Big Bang, eventually we'll have heat death. Heat death is a phenomenon where energy keeps spreading out infinitely, and your stars turn into black dwarfs, and they essentially are pieces of rocks, and nothing happens. But that's just one of the theories. Another theory could be that it flips and then it starts shrinking back in, and you have an unrelenting cycle of expansion and contraction. But all of these things, now that we think about them, there's nothing we can do to stop them, there's nothing we can do to affect them. We can only ever learn more about them. And learning more about them affects the way how we live our life today. Thank you. Any questions for any four of us?
I really like the Einstein quote before. I just wondered what side you're on. Is everything a miracle or nothing?
This one.
Yeah.
I think everything's a miracle if you want it to be, but even if it isn't, you can make it one.
Good answer.
Write that down.
That'll be on a slide one day.
Without putting you on the spot too much, can you tell us a little bit about the Higgs boson?
Oh, sure. You didn't put me on the spot there. What's really interesting about the Higgs boson is something called the field theory. The field theory is that every one of these force particles exists in a field. And whenever one of these particles interact with that field, they all have domains. So, for example, a strange quark has something called strangeness. And the strangeness is a property that's always conserved in interactions. So there's a field that exists for that strangeness, and say an electron can't interfere with it. Similarly, there exists a Higgs field, and any massive particle can interact with that Higgs field, and because it interacts with that Higgs field through the Higgs mechanism, it triggers essentially giving the particle mass. So to give an analogy, it's like dominoes. You have a state of dominoes toppled over, or a state of dominoes not toppled over. And once the dominoes have toppled over, you can't untopple them. But dominoes toppled over is a more stable state than standing dominoes. Similarly, when you have a Higgs mechanism being triggered, it gives the particle mass. And that mass is a more stable state than having no mass. That's my best understanding of the subject.
Thank you.
Any other questions regarding the standard model of black holes?
There's actually one thing I love the most about this model, and it's the fact that it's fine. I'll just point. It's the fact that all the matter we see in our daily lives, this book, this chair, humans, you only need an up quark, a down quark, and an electron to describe it. So the rest is essentially in our daily lives have no use. The muon and the tau are again heavier, like think of them as heavier isotopes of electron. They have the same charge, but again they have different masses. So in this case, the masses are represented by like E equals M in the format of E equals mc squared, where this is their energy in electron volts, which we have learned in physics, and that's c squared. So all of these particles, they have really small masses, and basically they can make up anything. Now I think that's a fascinating thought. How can you take billions of something that amounts to nothing to produce something which is amounts to something essentially? And this will, I guess, puzzle physicists for like years to come. And I actually attended the Carlo Rovelli's talk on white holes at the RI a few months back. And what he told the audience was physics is nothing but an ego check. Like we used to think we were like gods, just doing anything we wanted. But we now realized we are nothing, we are insignificant. And he said his book, 7 Brief Lessons on Physics, it's just a collection of instances where humanity thought they were right, and then they just turned out to be completely wrong. Thanks.
Thank you everyone for coming. thank you very much to Malhar, Mitul, Mayor, and Vange. That was really amazing. I think in particular the space-time walking thing, that was really useful. And entropy is very, very difficult to explain. I think you did a very good job there, Malhar, so well done. The book, 7 Brief Lessons on Physics, is currently out of the library, but I've just spoken to Helen. I think we're going to get some more, so if you want to see the book, please come and check it out from the library here. Thank you all very much for coming, and can we give one more round of applause?
Cheers to entropy.